The module is quiet. The crew is in the sleep cycle. The atmospheric monitoring board shows all green. Oxygen nominal. CO2 nominal. Behind panel 14C, something has been burning for 40 minutes. It produces no smoke column. It triggers no ceiling detector. It emits a faint blue glow the size of a golf ball behind a sealed access cover. The ventilation intake 3 centimeters from the burn site has been delivering its output to the crew cabin for the last 38 minutes. The CO reading on the monitoring board has not yet moved. It will. Spacefire doesn't rise to the detector. It drifts to the crew. On Earth, that sentence does not make sense. Fire rises. Smoke rises. Hot gas rises. You mount detectors on the ceiling because the ceiling is where the evidence goes. Every instinct, every training protocol, every piece of hardware in a standard fire response system is built around that one physical fact. Remove gravity, and the fact disappears. The fire does not rise. The smoke does not rise. The combustion products do not go anywhere except where the air happens to carry them, which in a sealed spacecraft is everywhere the ventilation system reaches, including the breathing air of the sleeping crew 4 meters away on the other side of a wall that shows nothing unusual. The difference between an Earth fire and a microgravity fire starts with shape and works outward from there. On Earth, combustion heats the air immediately surrounding the flame. That hot air becomes lighter than the cooler air nearby and rises, which is not a small detail. It is the entire operating mechanism of fire as most people understand it. The rising column of hot gas pulls fresh oxygen up into the flame base from below, feeding the reaction. It simultaneously carries combustion products, carbon monoxide, carbon dioxide, water vapor, unburned particles, upward and away from the reaction zone. That vertical transport is what makes fire visible from a distance, what makes smoke detectors work, and what gives fire its characteristic shape, the stretched teardrop, wide at the base where fresh oxygen arrives, narrow at the top where the hot products escape. In microgravity, the rising column does not exist. Hot air does not become lighter than cold air in any way that matters without gravity to sort them by density. The flame has no convective engine. It cannot pull fresh oxygen in from below or push combustion products away from above. It must feed entirely by molecular diffusion, the slow, random drift of oxygen molecules from the surrounding atmosphere into the reaction zone, and the equally slow drift of combustion products outward in every direction. The flame becomes a sphere because diffusion operates equally in all directions. It burns cool because the reaction rate is limited by how quickly diffusion can supply oxygen. It burns blue and nearly transparent because the lower temperature produces far less of the glowing soot particles that give Earth flames their visible orange color. A crew member conducting a visual scan of a darkened module can look directly at a microgravity flame the diameter of a golf ball and see nothing their threat recognition system registers as fire. The flame also does not self-extinguish from local oxygen depletion. On Earth, a fire in an enclosed space will eventually consume the available oxygen near the flame and suffocate itself. In microgravity, the combustion products drift outward as the oxygen drifts inward, maintaining the oxygen gradient at the reaction surface indefinitely as long as any oxygen remains in the module atmosphere. The flame also does not self-extinguish from local oxygen depletion. On Earth, a fire in an enclosed space will eventually consume the available oxygen near the flame and suffocate itself. In microgravity, The combustion products drift outward as the oxygen drifts inward, maintaining the oxygen gradient at the reaction surface indefinitely as long as any oxygen remains in the module atmosphere. A microgravity diffusion flame in a pressurized spacecraft module with normal atmospheric composition has access to the entire module's oxygen supply. It consumes that supply slowly, continuously, and without any visible sign that it is doing so. February 23, 1997, Mir Space Station. 6 crew members aboard, 3 Russian cosmonauts, 2 Americans, 1 German. A Vika solid-fuel oxygen generator canister in the base block module ignites during routine activation. The canister is designed to produce oxygen by burning a chemical mixture. Under normal conditions, the process is controlled and the output is breathable oxygen. This canister does not produce breathable oxygen. It produces a sustained burn that lasts approximately 14 minutes, generating dense smoke that fills the base block and propagates through the connecting tunnels faster than the crew can move through them. One of the 2 Soyuz evacuation capsules, the crew's only means of leaving the station, is on the other side of the smoke. For the duration of the event, half the evacuation options are physically blocked. All 6 crew members are exposed to combustion products. Respiratory protection equipment is deployed. The fire self-extinguishes before the situation becomes unrecoverable. The crew survived because the fire ran out of fuel before the crew ran out of options. That margin is not an engineering success. It is the documentation of how little distance exists between a manageable event and an unrecoverable one. The Mir fire lasted 14 minutes. The smoke blocked an evacuation route within the first minutes of ignition. The crew's survival depended on a variable, how long the canister would burn, that they could not control and could not predict. Every crew response protocol that existed before February 23, 1997 was written for a fire that rose, produced a visible flame, and responded predictably to suppression. The fire on Mir did not do any of those things. It told the engineers who analyzed it exactly what a microgravity fire actually does to a crewed module, and the analysis produced changes. Not enough changes, and not fast enough, but the documentation existed from that point forward. Behind panel 14C, the flame is feeding on the outer insulation jacket of a power cable. Cable insulation is present in every module of every spacecraft ever built. Meters of it running along walls and behind access panels, out of sight during normal operations, unreachable without tools during an emergency. The flame sphere sits against the cable surface at the point where diffusion can deliver enough oxygen to sustain the reaction. It does not spread rapidly. It draws oxygen from the module atmosphere and releases CO directly into the same atmosphere at the same rate the ventilation system circulates it. The CO monitor on the crew cabin wall is calibrated to alarm at a threshold designed for rapid, large-scale combustion events. A slow, smoldering sphere behind an access panel does not cross that threshold quickly. It builds toward it. At 200 parts per million of CO, a sleeping crew member begins experiencing physiological effects without waking. Headache developing slowly, oxygen delivery to the brain slightly reduced, sleep quality degrading in ways that feel like ordinary fatigue. At 1,000 parts per million, cognitive function is measurably impaired. Reaction time slows, judgment degrades. The ability to execute a memorized emergency protocol under stress is reduced precisely when that protocol is most needed. The monitoring board does not show 1,000 parts per million. It shows a number that has been climbing for 38 minutes and has not yet reached the alarm threshold calibrated for a different kind of fire. The first crew member to wake does not wake because of an alarm. She wakes because she has a headache. The module smells faintly different. not like smoke, more like warm plastic, easy to attribute to an equipment anomaly. She is mildly disoriented. Her visual scan shows nothing unusual. The monitoring board is not alarming. She logs the smell and returns to sleep. The CO reading climbs another 30 points in the next 12 minutes. When the alarm finally triggers, the extinguisher is deployed at the source location. The extinguisher is a directed stream device built for a fire with a stationary location. The flame behind panel 14C is no longer behind panel 14C. The ventilation current moved it 3 meters along the cable run during the previous hour. The panel is removed. The discharge contacts the spherical flame and does what a gas jet applied to a floating sphere always does. It moves it. The sphere drifts to the opposite wall, contacts a cable tie bracket, and the reaction continues on a new fuel surface. The extinguisher empties. The module atmosphere now contains suppression agent residue, accumulated CO from the original burn site, and an active flame that has not been extinguished. The obvious engineering response is better sensors, more sensitive CO monitoring, positioned at ventilation intakes rather than on walls and ceilings, calibrated to detect the slow CO rise of a smoldering diffusion flame rather than the fast rise of an open fire. This is the correct direction, and it is where post-mirror analysis pointed. It is also the direction that collides with a behavioral adaptation that cannot be engineered away. A CO monitor sensitive enough to detect a smoldering cable fire behind an access panel will detect CO concentrations produced by sources other than fires. Human metabolism produces CO. A crew of 4 in a sealed module generates measurable background CO from respiration and normal biological processes. A sufficiently sensitive alarm will trigger on that background during routine operations, during vigorous exercise, during cooking. Crews on long-duration missions adapt to alarms that trigger frequently without producing visible threats. The same adaptive pattern documented in every industrial environment where nuisance alarms are common. The alarm that experience has trained the crew to investigate casually is the alarm that triggers during the real event. Raising the threshold eliminates the nuisance alarms and restores the detection gap. The engineering problem is not solved by adjusting a number. Total flooding suppression addresses the extinguisher problem directly. Instead of a directed stream, a total flooding system releases suppression agent simultaneously throughout the entire module volume, surrounding a spherical flame from all directions at once, regardless of where it has drifted. This reliably works for microgravity fire suppression. It also renders the module atmosphere temporarily unbreathable for anyone inside at the time of discharge. Total flooding cannot be deployed while crew members are present without full respiratory protection, which means the protocol requires confirmed module evacuation and donned protective equipment before the only reliably effective suppression method can be activated. In the scenario where CO has already crossed the cognitive impairment threshold for at least one crew member, the prerequisite steps for the one method that works are the steps that compromised cognition makes hardest to complete correctly. NASA's Artemis program is developing habitats for lunar surface operations and the transit architecture for crewed Mars missions. A lunar habitat operates at 1/6 Earth gravity. The convective behavior of fire at that gravity level, where buoyancy is present but far weaker than on Earth, has not been fully characterized at the habitat scales Artemis is planning. A Mars habitat operates at roughly 38% of Earth's gravity. Flames at that level behave differently from both microgravity spheres and Earth standard teardrops, producing shapes and behaviors that no operational fire training has fully prepared a crew for. The detector placements, suppression designs, and crew protocols for those gravity environments do not yet exist in tested, validated form. The fire does not need to be large. It does not need to produce orange flame or rising smoke or a triggered ceiling alarm. It needs a fuel surface, an oxygen supply, and enough time in a sealed atmosphere. Behind panel 14C, all three conditions have been present for over an hour. The monitoring board is still climbing. The ventilation system is still running. And the question that Artemis and every habitat design program after it will eventually have to answer in validated hardware rather than planning documents is whether the detection system, the suppression system, and the crew protocol will all work correctly at the same moment in a gravity environment they were not designed for, on a fuel source that does not look like fire, at an hour when the crew is asleep.